Welcome to this video on interpreting exponential graphs and equations. By the end of this video, you should be able to interpret an exponential graph, find the domain and range of an exponential function in a real-world context, and evaluate a real-world problem at a given value of the domain. All right, so let's go back. This is our basic exponential function equation. The thing that you want to know about this is this A value represents the start amount. That's your y-intercept. So that's your start amount, which in the real world is the y-intercept. Okay? The b is what's being multiplied, and the x is usually defined in each problem. A lot of times it's time. Okay, so let's just kind of look at a couple of these, and I do want to remind you about the domain though. So up until now, most of our graphs have been all real numbers for the domain. But in a real world problem, the domain is restricted to the first quadrant. So in most cases, the domain will be greater than or equal to 0, because in the real world, it starts at the y-axis here to be in this first quadrant, and the x value there is 0. So let's take a look at this first scenario. So bacteria growth in a culture has a growth rate of 35% and is modeled by the function b of t equals 9.8 times 1.35 raised to the 2, where t is time. Okay, the graph of the function is shown. How many bacteria are in the dish at the start? All right, so something that's important to note is a lot of times you're going to be given an equation. So in this case, this is the equation that's given to us. Okay, and that should be the equation of that graph. Now, so for the domain, that's my x values. Okay, the x value right here is 0. And I notice on the other side, it's never going to stop. So that just means all of our x values are greater than or equal to 0. Okay, so that's our domain because we're starting at 0 and it's never stopping going right. Now our range, our lowest value in our real world scenario is right here at 10 where the graph hits the y-intercept. So all of my y values are going to be greater than or equal to 10. All right, and that's because that would be the starting amount for this problem, the y-intercept. So that helps us with this next problem. How many bacteria were in the dish at the beginning? Well, there were 10 bacteria at the beginning. And then how many bacteria are in the dish after 6 years? Well, let's look. This is time in years. So here's 6. I'm going to go up and I'm going to go across, and it's like just short of that 60 there. So here's what I'm going to do. I'm going to take that equation. This 2 is really a t. That's your t value, your time. So 9.8 times 1.35, and I'm going to put a 6 there. So I get an exact, I can look on here and I see it's about 60 million. But let's take a look. When you put that in, I got 59.3 million. So after 6 years, there were 59.3 million bacteria in that dish. Okay, and you can see the line is just below the 60 there. So that makes sense. All right, let's try it again. So we have a population of squirrels, and it doubles every year. Initially, there were 5 squirrels. A biologist studying squirrels created a function to model their population growth as p of t equals 5 times 2 to the t. So they gave us an equation here, okay, where t is time. So we know that t is time, and the graph of the function is shown. So here's the graph that goes with this scenario. Now, what is the domain? Remember, domain is your x value. So this graph does not go into this second quadrant. It stays in the first quadrant. Your x value there is 0, and there's an arrow on the other end. So it never stops going to the right. So your domain is going to be greater than or equal to 0. So what is the range of the function? The range of the function remember, you got to start at your start value. Well, we can't really see easily here, but if we go back and look at our equation, remember this A value is your start value, and then it does say initially there were 5 squirrels. So you can see that those match. So this is at 5, and all my y values are greater than that 5, so y is going to be greater than or equal to 5. How many squirrels were in the initial population? Well, they did tell us that right up here on the word problem. It started with 5, and you can see it in our equation, the 5 there. And then estimate the population of squirrels after about 2 years. So this is 2.5 years, so 2 years would be just before it. It looks to be about 20, but we can check for sure because we have the equation. There's 5 times 2, and our time that we're talking about is 2 years. And if you put this in your calculator, you'll get 20 out. So 20 squirrels after about 2 years. All right, let's try the ones on the back and see how we do. Okay, so here's some more examples from word problems, doing some interpretations when we don't have the graph in front of us. So from 1990 to 2000, the population of California can be modeled by P equals 29,816,591 times 1.1028 raised to the t, where t is the number of years since 1990. Okay, so we have the equation, okay, and it says t is the number of years since 1990. Okay, so if it was 1995, our time would be 5 because it'd be 5 years since 1990. Well, let's see what the question is. What was the population in 1990? Well, this started in 1990, so they're really saying what is our initial value for our population. Now remember, the initial value is in the A position. So when I look at my equation, that's my initial starting value. So the population in 1990 was 29,816,591. All right, so that wasn't too complicated. Let's look at number 4. So the population P of deer in a state's forest is modeled by the function P of t equals 200 times 1.34 to the t. All right. So we have that. Where t is the number of years since 1970, there it is again, years since 1970. So you're not going to plug in the actual year, you're going to plug in the number of years since 1970. If this trend continues, what is the population in 1975? So how much time has passed from 1970 to 1975? That would be a time of 5 years. So we need to be plugging 5 into our equation. So we're going to take our equation and we're going to plug 5 into it. There's only one variable spot, so that's the place it has to be. So when you put this into your calculator, you would have gotten 864.1, but we're talking about population, and we're not going to have a point anything for a population. You need whole things. So we're not going to round down to 864 because we actually started into another person with the decimal. So if we're people, we always are going to round up. So this would be 865, and in this case it's deer because these are living beings. So we can't round down on a living being. All right, the last one. The half-life of phosphorus 32 is about 14 days. The amount A in grams of radioactive phosphorus 32 that remains in a sample after T days is given by this equation. So here's this equation. So here's the thing, you don't have to know about half-lives or any of that. They give you the equation, okay? Then the question is asking how much phosphorus 32 is left after 10 days. So that's your time value, 10 days. So when I look, there's only one place that this can go. So we're going to plug it in. 400 times 1/2. The 1/2 represents the half-life. That means it's multiplying by half each time. And then it says T for time divided by 14. So we just plugged in the time that we were given. And when we put that in our calculator, we get 200 43.8, and remember that this is in grams, so we're going to put grams there. All right, so hopefully that was helpful to you. If you have any questions, let me know, and I'll see you in class.